Right, the first thing we have to talk about before looking into the loads and seeing which is the required thickness for each part, I'm gonna talk very quickly about the materials we can use. So typical materials used in sound rockets are um, well, let's see, no, another color, aluminum, and then steels, maybe titanium, alloys, titanium, and then composites. So in this area we have, yeah, it's a whole subject by itself. We have glass composites, uh, graphite. It's a very extended subject, and I'm not gonna cover composites here. It's trickier to manufacture. Can be more costly. Well, it's more advanced kind of compared maybe to aluminum and steels. So the nice thing about composites is the weight is probably going to go down if you compare them to aluminum and steel. So if you wanna cut down the weight, composites are the way to go. But manufacturing process is much more complex. A lot of time, it's going to be way more expensive. So, and titanium, I'm just going to mention it, but yeah, it's about, you know, a same part made of titanium or aluminium, maybe titanium in total, counting the material and the machining, can be 15 to 20 times more costly. So titanium is pretty expensive. So yeah, I'm just gonna mention it, but I'm gonna focus mainly on aluminum. Steels, you know, the strong steels are pretty hard to get your hands on. So yeah, I'm basically narrowing down to aluminum, but yeah, a couple of concepts I guess you already know, but ultimate strength and yield strength. If you don't know what this is, well, yeah, you should look that way before going ahead with this video. So let's see, aluminum. If you're not already familiar with all the alloys and well, metals in general, there are tons of alloys, mostly on steels. On steels you have thousands of alloys, and the mechanical properties are going to change a lot between these alloys, and also the physical properties. So let's make a quick distinction of these three. So let's say I'm going to compare. You know, this is very general. You're going to see him just put in aluminum alloys, which is super vague, and steel is even more vague. Even titanium has a lot of different alloys. Normally, titanium alloys are like grade and then a number. So from grade 1 to grade 5, there's a whole world of difference. Totally different properties, manufacturing processes. So there's a lot of difference between inside of these categories. But still, let's generalize a bit. Cost. Well, let's see. Aluminum is around €5 per kilo, more or less, for a solid rod. Steel, well, it can vary a lot. I'm not talking about, by the way, tubes. Tubes go differently. Normally they don't go so much by weight. So, but order of magnitude, yeah. Steel, there's a lot. Well, I don't know how to categorize right now quickly the steels, but we could make a quick distinction of stainless steels, and then just well, let's say what you call just iron, you know. So stainless maybe is around maybe from 6 to 8 to 10, depending. Inside stainless we have a lot of alloys. We have 304, 316, 300, and you know, but more or less this is order of magnitude for stainless steels. Then for iron, so steels that do rust, well, the price is way lower. Maybe it's 4 times lower. This for stainless. Yeah, for let's say iron, well, I don't know, maybe €2 per kilo. So it's cheaper than aluminum. But remember that aluminum, the density is around 2.7 gram per cubic centimeter, and still we're looking at maybe 7.8. Titanium, maybe it's 4 point something. Don't use it that much, so I don't know, around 4. And the price is, yeah, it's super high. Maybe 15 times more than aluminum. It's just crazy high. So yeah, unless you're a millionaire, I don't think it's gonna be hard using titanium extendedly on a student project. So then for the ultimate stress, aluminum varies a lot. Normal bad alloys maybe have ultimate stress of maybe 300 megapascals. This could be 6000 series. I'm gonna describe these further on in the next video. Well, in this video, just doing an overview. Maybe 2000 series. Well, 2000 are stronger, but 6000, and then 7000 series. Maybe you can reach 550 megapascals. And in steels, well, it varies a lot. Stainless steels can go around 700 megapascals, kinda. Then we have high strength steels that can go above 1000. Okay, we have for example 15.7 molybdenum steel, but it's hard to get these kinds of materials. So aluminums, it's really easy. Yeah, and standard stainless steels and iron, it's easy to get your hands with some of these. With high strength steels, yeah, they're more rare. And titanium, on the typical alloy, which is grade 5, we're looking at maybe, I don't know, from 800 to 900 megapascals. So it has a strength comparable to pretty high strength steels, above stainless steels, and it has half the density. So that's why you can imagine why it's such an interesting material. Plus, the temperature ranges of titanium are around the same of steel. You can use these guys at really high temperatures, like above, maybe up to 800 or 600, 800. What about aluminum? Aluminum from 200 and 250 it doesn't melt, but well, the mechanical properties are going to drop a lot at these temperatures. So yeah, hopefully with this quick table you can get an idea of the basic differences. Maybe we could talk about also the conductivity of these materials. Aluminum, as you know, is really conductive, maybe 200 watts. Is it meter Kelvin? Yeah, I'm not sure about the units. Steel was iron is maybe 30, and then stainless maybe it's 15. So it's still thermally conductive, but look, it's one order of magnitude below aluminum. Aluminum is considered very, very conductive. Just yeah, the second most conductive material. Like, well, not the second most, but from the common, let's say the common materials, copper is 400, I think. But aluminum is still really, really high. Titanium is lower, maybe half the one of stainless. I'm not quite sure of this. Maybe it's 8. Just not quite sure. But so maybe the idea, because steels are going to weigh so much more than aluminum, you're probably not going to use them unless you can get your hands with some high strength steels. You're not going to use them unless it's some parts of the structure where the thermal loads are going to be present, are going to be important. So if you're constrained by these temperatures of the aluminum, then steel is the way to go. So for high temperatures, yeah, steel is going to be your friend. But apart from that, the density, as you can see, is really high. It's 2-point-something times higher than aluminum. And the strength, you have really high strength aluminums that compete with steels. So the high strength of steels normally are not gonna compensate. I'm talking about standard materials again. So let's see. Should we talk about maybe aluminum first? Aluminum. It's nice because the alloys are pretty standardized. We have the typical alloys are the following. We have the 2000 series, maybe the 6000 series, and the 7000 series. Okay, so each of these series are going to be aluminium with another metal. Each of these alloys are going to be alloys of many metals, but primarily it's going to be aluminum and another metal. I think this is magnesium. This is zinc, if I'm not wrong, and 2000. Can't recall. Sorry. So these two are the most typical aluminum alloys. So very typical. These series are maybe 2030, 2007. These are typical. And then the ones that are most interesting are the 2024. Maybe 2024 is relatively easy to get your hands with, but then we have the alloy that was used in the space shuttle, I think the main tanks, 2219. For these, for the typical, let me let me finish this first. So for the 6000 series, typical alloys 60, 60, 60, 63. These are the standard alloys. So these are like the you know, the bad alloys, but the ones you're gonna find in any kind of provider that sells aluminum. These are standard alloys for tubes and for rods. Maybe 60, 82. And then 6061 is, I see it everywhere, considered like an aerospace alloy, but it just has properties slightly better than the standard alloys. So these typical alloys, these its ultimate strength is going to be around from 200 to 300 megapascals, and maybe 6061 is maybe just slightly above 300, but nothing special. There's nothing special about 6061. By the way, each alloy then has a heat treatment, so it's not the same to have this alloy. The alloy, after all, is just the composition of the material. So it's 8% zinc, 93% aluminium, whatever. Then the heat treatment, which is like the surname of the alloy. So maybe 6061 T6. Well, this means it has follows specific heat treatment, which can make the alloy stronger. So the heat treatment can change a lot the mechanical properties. So you have to look into that as well. It's not the same as 6061 T3 than a T751 or I don't know whether all the heat treatments by heart, but it definitely changes a lot the mechanical properties. So take that in mind. So these are the the typical alloys, okay? And then should we call this aerospace? I don't know. Strong alloys. 2024, 2219 on the the 6000 series. I don't think there's a strong alloy, not that I can think of right now, but on the 7000 series there's the famous 7075 alloy. This alloy is like it's way above the ultimate strength of these. Okay, that's quite above these ones as well. So these alloys, by the way, the price is kind of similar, although the 7075 is you're gonna see it's way stronger. We're talking about maybe 570 megapascals of ultimate strength at room temperature, and these two maybe 450 megapascals, more or less. Although the change is super high between these alloys, the price isn't that different. Maybe these are around €4 per kilo. Maybe this is 5 point something. Same with these. The problem is tubes. I can't find tubes with strong alloys. So tubes only come with these two alloys. So that's a problem. So at least in Spain, I can't find any. Any tubes. So if you want to make a tube out of a strong alloy, well, I don't know. There are different methods you could do. You could spin. You can spin it, but it's pretty expensive. Or probably you just get a rod and make just drill it. For For larger diameters, that's not gonna be very cost efficient. But I don't know if it's something that it's the same in the rest of the world. But yeah, I've had a hard time finding tubes. So what's the difference between these two? Well, it's why would you choose a Series 2000 over a 7075? Well, they're pretty similar, but these guys are slightly more heat resistant, just slightly. Better properties at high temperature, slightly. You're gonna see that I told you that aluminum, the maximum temperature of working temperature is maybe 250 or so, because although the aluminum melts around 600 degrees, if you check the ultimate strength, versus temperature, it's gonna look something like this. This is room temperature. Let's put 20 degrees. 100. Yeah. It's gonna look something like this. So let's plot out maybe normal alloys. Here I'm gonna plot, well, normal alloys. No, I don't like this. Let me redo this. Let's put here 100, 200 megapascals. This is megapascals. 300. Oops. So let me plot like first a normal alloy. Maybe at room temperature is around 300. Then at 200, maybe it's already at 100 megapascals. So it's gonna look maybe something like this. Then at around 250 megapascals, degrees centigrade, sorry, it's gonna be maybe around 50 megapascals. This is nothing. So this is normal alloy, 6060, 6063, 2011, blah blah blah. What about 7075? Well, 7075 is really strong. It's nearly double typical alloys on room temperature, but it does something like this. At about, well, it doesn't go below, but at about 150 degrees, it's the same as the rest. So it's gonna be interesting if we're working at below maybe 150, more or less. And then the 2000 series, the strong 2000 series, going to be something like this. Maybe they're a bit stronger than the rest in higher temperatures, just slightly. So I put maybe 2024 and 7075. So yeah, the main problem with aluminum is the temperature. So if you're gonna be flying at high mag, it's gonna be a big issue, because you're gonna have to design your rocket taking, of course, the least ultimate strength you're going to expect. So if you're expecting the rocket to reach 150 degrees, well, you're going to have to take this ultimate strength, which is really low. And yeah, so don't get too happy with these values, because this is only room temperature. So you can find more data in the internet, and the same for steel. For steel, it also loses mechanical properties with temperature, but not so sudden as aluminum. So yeah, that's a big disadvantage over, well, with aluminum. You just have to take that in mind when designing the rocket.